Thanks a lot for the introduction. As Demetrius said, I'm Todd. I do ML at Google. This is some work, as it was pointed out, quite correctly, some clickbaity work that was done with my colleague, Niall Murphy. I've been doing machine learning stuff at Google for about 12 years here in the Pittsburgh office. Niall has spent the last 15 years working for Amazon and Google and Microsoft and has done a bunch of machine learning stuff as well. And Niall, you may know from his role in creating and as the lead author of the SRE book. So if you don't know that, that's fine. By the end of this talk, you'll be convinced to know that. I don't know if you will. So the title was, yes, the only truly difficult problem in machine learning, but that's, of course, nonsense. Really, that's an exaggeration for effect. I want to talk about the only truly difficult problem in machine learning: reliability, operations, and production. And again, even that's an exaggeration, of course, but people only come to things that are a little bit exaggerated. But I do want to point out that there are a lot of problems that we have that are not machine learning problems. And there are already good solutions for those. And that's the punchline, is that I want to point out a bunch of problems that aren't really our problems as MLOps folks and have already been solved pretty well by some other people so that we can focus on the problems that are our problems. So we have many problems. We have so many problems to choose from. So MLOps generally concerns itself with producing reliable, high quality ML systems. But these are, of course, complex, interdependent, multi-stage pipelines. When you hear stories like the one that was just told about a model that has to work on a lot of data in order to stabilize, but that doesn't show up until you actually put it into production, that stuff is pretty common for us, right? So that complexity in the interdependence is really what we're looking at in these multi-stage pipelines. And so the thing I want to convince you of is that we already have techniques in computing, and in particular in site reliability engineering, for addressing these. And if you don't know what site reliability engineering is, don't worry, I'm going to explain it, or explain it sufficiently well that we can pretend we all know what it means. So let's talk about machine learning production problems, but let's express them in terms of what we would like to achieve. So for those who haven't seen this term, SLO, a service level objective, it's just something we want to be true in the world. And when you express it that way, then you can build a system that tries to accomplish it, and you can build monitoring and emergency response that tries to achieve that. So let's talk about like training pipelines. What do we want from a training pipeline? If you're sitting around, you're like, well, I want my models to finish training on time. So finish is the good part. And then on time is whatever on time means for you. It could mean a particular speed. It could mean by a particular deadline. It could just mean before you wake up the next day. But on time for you, we want our model configurations that are updatable, are durable, so we don't lose them. They're probably versioned. We can troubleshoot them, and they work. When I say like and functional, they work. They create models that work. And we want these trained models that result from our training to be usable in some format, broadly usable. So are they correctly formatted? Will they load into the next stage of the pipeline? Do they have reasonable quality? We're coming back to quality in a minute, so keep your attention on that. What about the data ingestion system? Well, we want the data to be readable, correctly formatted, interpreted. We want data that are ingested quickly, right? We don't want to sit around waiting for the data to appear. We only want data that are accessible and only accessed by the right users in the right program. So a lot of us deal with some data that's pretty private, which is great. Like that's fine, but you need to treat it appropriately. So you need to restrict access to it, and you need to log that access. Okay, good, sounds good, right? What else? Oh, we're going to have some sort of feature storage system, right? Here we are at this gathering. We've heard a little bit about some feature storage systems. But we don't just want to store features, I think we want to store features. We want to store model snapshots. We want to store configs. We want metadata about all of that stuff. That doesn't have to be one system, but it certainly, all of those needs have to be met somehow. And if not, we're just slapping things in directories and hoping for the best, which is also fine. But like, you just have to acknowledge that is your storage system if that's what you're doing. We want features that can be read quickly and reliably. We want configs that can be updated and validated for all of our storage systems. And we want the data to be durable and correct. Durable for people who don't do data integrity stuff just means we don't lose it. It's a fancy way of saying data we don't lose. Okay, cool. Serving system, we want queries to be fast. If we're looking up stuff, we want them to be fast, whatever fast means, and error-free, whatever error-free is acceptable. Not error-free, but low error, really, I should have said, whatever low is acceptable for you. Models that are updated, if you have a new model, you want to replace it in serving, it should work. We want query logs because we're probably going to use whatever questions and answers we asked about the model for training the model in the future as some kind of exogenous signal of what the model's doing. So many MLOps folks claim to have or do this stuff, right? So like we've seen a lot of systems and a lot of pitches and a lot of methodology that says, like, we're going to solve these problems in this way. We're going to have end-to-end automation of the ML lifecycle. We're going to focus on efficient sharing of compute resources, optimize your data storage, improve and standardize data ingestion, all of this stuff. Like, these are the kinds of things that many MLOps products and services claim to address. And this is the kind of work that many people who say that they are doing MLOps are doing. So that sounds fine. Like, that's just, here we are. This is our community, and these are the problems we're solving. So what I want to do, though, is take a step back and say, actually, these are not our problems. These are somebody else's problems. We can solve them, but we shouldn't pretend that this has anything to do with ML, because most of what I just described are not MLOps problems. They're just software operations problems. They're just the kind of problems you have when you're operating large-scale distributed data store, when you're operating a web crawler or a web page that you serve, or a payment system, or any of these things. Like, the ML part is not what made most of those things hard. And so as a result, I want to take a step back and say, let's be lazy here. If somebody else already solved some of these things, or at least has good approaches for ameliorating these things, we should take advantage of that, right? Like, why reinvent things? Sounds good. So who has solved some of these things? Well, I know some kids who have done so. They're called SREs. So let me pause for a second and say, well, what is SRE? SRE, site reliability engineering, is an approach to doing large-scale systems engineering at Google. Started at Google, and now it's like, a lot of different people throughout the industry have adopted this approach. And it basically treats operations problems as software problems. So apologies for that. That was terrible. Hold on. I am really so sorry. Ugh. Terrible. I've lost my window. Everything is awful. There we are. Hopefully we're sharing again. So SREs treat operations problems as software problems. And there's sort of the approach that Ben Traynor, who is an early exec at Google, approached reliability engineering. So that's fine. So let's look through what is the bag of tricks that SRE has to solve some of these operations problems as if they're software engineering problems. So what are the kinds of things that SREs do? Well, we design redundant infrastructure. And I say we because, like, I am, in fact, do SRE work for ML. So we design redundant infrastructure. We treat configuration as if it's code, because it is code. It determines the functioning of software. We use distributed consensus. Not enough people really take that seriously, and it's really the only way to have sane distributed computation. Lots of focus on security controls and how those work. Enormous amount of focus on monitoring and observability. Lots of techniques for thinking about whole collections of computers as if they're one fleet rather than individual computers. These are all pretty straightforward approaches. Sounds good, right? So let's take a look quickly at how these map onto the problems that I just said were MLOps problems. Well, we see training pipelines. Those are the service level objectives we were trying to achieve. So how do we get models to train on time? Well, we monitor model completion and progress at various stages throughout the pipeline, and we alert when it's not. It's not magic. And that actually has nothing to do with machine learning. If you're processing a bunch of payments, or you're indexing a bunch of data, you have exactly the same problem. Similarly, how do we check our configs are any good? Well, we validate the configs. We write validations against them, and we make sure that those validations pass. Similar, Like if I have a trained model and I want to make sure it's correctly formatted and will load, well, I have a staging system where I try to load the model. And if it doesn't load, it is not valid. And so you might see the word model and think, what is that? Like, why isn't that the machine learning part of this whole system? But in this case, a model is just a bundle of software that needs to load into another piece of software, and it's either correctly formatted or it's not. So again, none of these problems is a machine learning problem. Similarly, data ingestion stuff. I won't go through all of these and we will share the presentation. But the point I want to try to make here is that as you walk through this, you'll see each of these, like, are the data readable? Are they correctly formatted? Not a machine learning problem. We should monitor that data ingestion is succeeding, that we're not throwing errors as we try to read it. We can, test load some of the data. We can run assertions on the data ingestion and validate that the formats are correct. We can check the access controls on the data to validate that we have restricted it. And we can do so periodically, like once a minute, once an hour, et cetera. We can log access and we can monitor those access logs. So again, no ML here. What about the storage system stuff? Same, right? Like none of this is about like, is a storage system working? Now, the distinction I want people to think through is the requirements we have for these systems are in fact machine learning requirements. Like, why do we want these things? We want these things because we're trying to build production-ready machine learning systems. That's great. But how we solve those problems now has nothing to do with machine learning. And that's an important distinction and an interesting one. Similarly, serving system. I mean, to be honest, the serving system is probably the least machine learning part of it. Like, it's a distributed serving system, similar to a distributed web serving system or many distributed application serving systems. The constraints that it has come from an environment of machine learning, but the way to solve those constraints, again, is by running a high quality, well-monitored distributed serving system. So nothing to see here. So here's an observation I'll make, and then we'll talk about what's left. So the observation that I'll make is that all of these solutions are context-free solutions. So they do not depend upon the fact that the work that we're doing is machine learning and the machine learning that we're doing is for some particular purpose. We don't need to know that to monitor the completion of our training pipeline. We do not need to know that to make sure that our models are correctly formatted and will load into our serving system. Right? We just need to know we have a process that is finishing, it is producing a binary artifact, and it needs to get to the next stage, and the next stage needs to start. And the fact that it is about targeting an advertisement or about predicting a purchase or about the objects that are in a photo, that's irrelevant to the kind of work that is done to make that production. So that's, I mean, I've mentioned this to other people, and sometimes people get annoyed or frustrated. They're like, you're trying to take away something from me. I'm like, no, I'm excited that we don't have to work on this stuff. I'm not saying no one has to work on this stuff, but when we work on this stuff, we are not doing ML ops, we're doing ops. We are not doing, machine learning reliability engineering. We're doing regular systems and site reliability engineering, which is great because there's a ton of people who know how to do that and they're good at it. And we should borrow from their skills. And we should actually have them on our teams. And one thing I'll say honestly, and we can talk about that, I know it's a question that Demetrius brought up with me when we spoke. Most of the people who work on SRE for machine learning at Google do not have a background in machine learning, and it's not a problem. In fact, it's not even vaguely necessary. It's not to say they don't need to learn some of that along the way for useful context, but most of the problems are not machine learning problems. Okay, so wait, so are we done? Like, is that it? Did we solve all the problems? Unfortunately, no. The whole point of this is not what is not MLOps, but what is. So what's left? So where's the machine learning and machine learning operations? I want to make an argument. It's mostly hidden in the data, and this is the problem. So subtle changes in the distribution of data, both in positive and negative sense, can have enormous impacts on the quality of our models. And the quality of our models is in fact what we're trying to do. So one of the themes that I've heard as people discuss these things is like, oh, like MLOps should really focus on the business value, the organizational value. Yes, right. Again, we're not here to train models. We're here to accomplish some higher goal, which could be, sell more widgets, or it could be predict more weather, and it can be identify more oranges in pictures. But whatever thing we're trying to do, that's the thing that is the point of the whole thing, right? That is why we're here. So what happens if we have subtle changes in the data is that they're very difficult to detect from a systems level, but have profound implications on a modeling and quality level. So in order to do that successfully, in order to mitigate those problems successfully, it is often necessary to have the whole picture sort of in focus in your monitoring, in your application, and that's very expensive. So let me motivate this with a little example, and then talk about what I think we can do, and then I'll wrap up. So here's an example. Consider some hypothetical machine learning system that we run on a website that sells yarn, right? Sells yarn for people who knit and crochet. Okay, so people search for things on this website, and we track the things that we show them and which ones they click on. And we use that as a signal to a model that tries to produce ranked results for a search engine as people are shopping for yarn. And maybe we use clicks, but we also use profit margin, right? Because we might choose to show something that isn't quite as popular for people to click on, but makes us a lot more money. I know that is base to say, but as a yarn seller, we might really want to make some money and want to cover our costs. And so we might do that. So now imagine that our app, like we are a global yarn seller, right? Like we are across the world. And for whatever reason, we have a system failure and we drop all of the logs from all of our Spanish language users. So we are no longer updating our model with the clicks that people whose browsers are set to Spanish are clicking on. So for our particular set, consider the possibility that this is only about 7% of our data. So if you're monitoring across your data, you might not notice it. Like that's well within the fluctuation of a normal daily cycle, right? You have these diurnal cycles and it would be difficult to detect that even. Okay. So what happens when we train the version of our model for the next day or the next hour or the next whatever, like we're going to update this model, our system will incorrectly learn that all results in Spanish are bad. That's not good at all, right? Like that's terrible. So as a result, our system will stop recommending Spanish language results, even for Spanish language users. This is really not good. So this is a common kind of a problem. It's not even a very interesting problem in some ways, but it is interesting to me because it motivates the question, if you didn't know this was a machine learning set of models, how would you detect that kind of an outage? And you say like, oh, well, I would monitor all the data arriving and make sure I had data. You're like, well, you would only know to look for data in Spanish if you knew Spanish was a valuable feature of the machine learning system, if you knew that was relevant. Similarly, if you knew that geography was relevant, you would look across geography. If you think time of day is relevant, you can look across time of day. But in each case, you have to know the machine learning purpose of the model in order to try to solve it. So note that this is a problem that is a modeling problem that's caused by an infrastructure failure. Okay, well, so now we know model quality can be impacted by making bad models. Lots of us have made bad models, and that'll continue, presumably. We're all trying to make better models, but usually start with the bad model. So we can have bad models made by modelers who have made bad models, but we can also have models that are made bad by infrastructure failures. And that's the class of problems I'm particularly interested in. So some infrastructure failures really will only easily or sometimes at all show up as model quality failures. I've listed a few examples of these, and most of you are familiar with some of them, so I won't go through them. But most of them have to do with cases where we have the data, but the mapping of the data to the meaning of the data, so the semantics have changed. Simple examples like I can change quantization of, if I have an integer for age and I quantize it on decade and somebody else quantizes it on 5-year boundaries, well then those just mean really different things. Like an index of 4 in that quantization is completely different and addresses a very, very different age for whatever that record is. And so whatever that example is. So you can imagine all kinds of things like this that are not, they're essentially invisible at an infrastructure level, but clearly visible at a model quality level. And so what I want to point out is that this leaves us with model quality monitoring is the only real end-to-end integration test of a machine learning system. And that is actually a little bit of a disappointing and terrifying result, because what it means is, as machine learning infrastructure engineers, we're not actually capable of building a system that is reliable in the true sense, because to be reliable in the true sense would be this system trains good models and puts them into production reliably. That is a wonderful thing to aspire to. That is not a thing we can achieve. And that's disappointing. And so the next step is, well, what can we achieve? Well, here are some best practices for model stability and monitoring. Most of these come from a paper that some colleagues of mine at Google, including the inimitable and well-known D. Scully, produced, along with Eric Breck and a couple of other collaborators in the Cambridge office, on the ML test score. And these are just straightforward ML test recommendations that they had. What I will say about these, I won't go through them all in detail because I'll leave time for a couple of questions, but what I will say about these is each of these is easier said than done. I included that note on the first one, but none of these is easy to do. So notify on dependency change, sure, that's great, but what's a change in a dependency? Like, how do I know if some data I'm consuming changed the meaning of one part of one column of data that I consume for my model? How would I even know that? But there are things that you can do that are relatively simple. So, you can look that you're not using massively more compute than you were using to do the same thing previously. You can keep track of how old your models are and that they're not older than you expect. So this set of solutions has a wide range, ranging from very easy and very straightforward, like keeping track of your model age is trivial. Useful invariants that hold across training and serving, that's quite a bit harder, because what is a useful invariant? And it's very context sensitive. So I think so what I'd like to leave you with, and then I'm happy to take a couple of questions, and I will also be on the Slack channel after this to answer other questions. But what I'd like to leave people with is a sense of sort of hope and dread. So the hope is that many of the problems that we think are really big problems, other people are already working on and have some good approaches to. Not to say, like, I am not saying like, oh, these are easy. They're not easy, but they're hard in a way that has attracted thousands and thousands of other people who actually don't know that much about machine learning and don't care about it to work on. And we should take advantage of their skills. So that's the hope, is like, oh, we can probably do a lot better with a lot of the things we're doing by following best practices for distributed systems and by hiring some of the people who already know how to do that and getting them to help us. That sounds great. The dread part is, and then what's left is model quality and the intersection between model quality and infrastructure. And that is just, there is not an easy way for that. So thanks very much.
That was awesome, man. That was exactly what I was looking for. Thank you, Mr. Todd Underwood. We've got some questions coming through in the chat. How do you visually monitor model quality?
Yeah, so I think, like, again, it's super context dependent. So if you have a model that's trying to make money, you graph how much money it's making. I mean, it sounds really straightforward, but like, what's the model trying to do? If you have a model that's trying to sell things, how much of what kinds of things is it selling? So you really basically determine the slices, so the subdivisions of significance for that model, and you graph it out on that. So if you have a global service that's trying to translate things, graph how many translations people are saying are bad around the world, et cetera. So this is the sad part, is every question like that is going to have the form, well, it depends. What are you trying to do? Sorry for that, but that's where we are.
The nature of the beast.
Yeah, what else?
That's what you get. There's one about how you Mr. Underwood, are implementing some of these best practices you speak of?
Yeah, so I think, so what we have done is like we grew machine learning SRE at Google out of SRE. It is not an outgrowth of Google Research. It is not an outgrowth of core systems. It's an outgrowth of SRE. And so in my organizations, I preferentially hire people who are good at distributed systems and interested in machine learning versus people who are interested in machine learning and willing to do some distributed systems. So that is one of the things I do. And I would encourage other people to do that, because I think it's a little bit offensive to us, but like, we just have to acknowledge you don't actually need to know as much about machine learning to do the production engineering of machine learning as people keep saying. Not to say it's not fun, it's not sexy, it's something we can do if we want to, but like the machine learning part, and part of this is being at Google, like the people who do that are so much smarter than me that I have no illusions that I'm going to be like that. Like those kids know what they're doing. I'm just over here. I'm just the machine learning infrastructure plumber, and I'm connecting up the pipes and I'm making sure that the bits are flowing through those pipes. And it just happens to be ML bits.
I love that outlook on it. Any thoughts on approximating model performance when you do not have ground truth labels or they are received on a delay? Best practices around that?
Yeah, so I think the important part of that question is the cheating easy best way is if you can get a golden set or you can get some ground truth. And so like, when you don't have it, I do want to say like, there's a couple things you can do, but man, if you can get a golden set, you can run your golden set through your model and say like, how's it doing? How's it doing for the new one versus the old one? If you don't have that, then I think in my experience, you take a big step back and you say, well, we do have one set of ground truth, which is what were we trying to do with the model? And there's only two answers. We don't know, or we know and it's X. If we don't know, it actually doesn't matter if your model's any good, because like it's fine for no particular purpose. Like not having a model is also fine. So you should probably close up your ML shop. But if you know what your model was supposed to be doing, go look at that, whatever that is. If it's supposed to make your factory run faster, is your factory running faster? If it's supposed to like schedule your meetings in the morning, how are your meetings scheduled? I know that seems glib, but that's actually like go back to what you were trying to achieve and find that exogenous signal from that and make it as close to real time as you can. And then beyond that, just compare the new one to the old one. Like once you have a little bit of confidence that you're not doing terribly, you can bootstrap quite a bit from that.
All right, last one, then we'll
Yep.
wrap it up. This one is, what level of infrastructure details do you expect from a data scientist to be able to know?
I think, it's difficult to answer that with precision, but what I love about that question is the implicit understanding that you don't get to be a data scientist without caring about the infrastructure. So I won't actually answer that question. What I'll say is I'm really excited that somebody asked that question, because what I'm hoping for is that more people acknowledge that they get to do the fun algorithm work and building the models, and they get to do the fun data analytics work, but they also have to care about how well it runs. And if they do, they're going to have a lot more fun, right? So what I would say is the more you care about production engineering as a data scientist, the more progress you will make in your data science work.
Todd, always a pleasure.
So good. Thanks for having me.
Muchas gracias. And
Claro que sí.
Also, I love that you have the creativity on the yarn piece is amazing to me. I was laughing when I was watching that.
All right, so little plug. That is one of the examples that we are weaving through the book that we're writing for O'Reilly. So you will see, I won't say the URL yet, but you will see that is an example that we use throughout the book. So that's why it was on my mind.